So it's my pleasure to introduce Sir Richard Faull to you this morning. I'm a bit of a fangirl actually, because I've really admired Richard's work for a number of years. He really doesn't need a lot of introduction, because I know he's going to tell you an enormous amount of stuff. But for those who haven't met Richard before, he is an academic and a neuroscientist at the University of Auckland, has been for a number of years, highly regarded. And a few years ago, and I know he's going to tell you a lot about it, he did start the Centre for Brain Research at the university, which is now a globally recognised institution. And as he's been telling us this morning, working collaboratively all around the world and bringing some of our brightest and best home as well to carry on their research here. So I understand a Taranaki boy originally, educated in Otago, but now up here in Auckland and doing amazing things. So it's my pleasure to introduce you, Sir Richard Faull.
Thank you very much. Well, it's a huge pleasure to be here. I'll keep my coffee here if it's all right. And you know, we are in the age of the brain. And you know, we've solved a lot of things in life and we're living longer, but you know, there's no point in living longer unless you know who you are and what you are, and you know who your partner still is. You know, when you wake up in the morning, I mean, it's critical. And so what I'm going to do today is just to give you, I've got 20 minutes to see, and I thought, oh, usually I speak for an hour and I always go over, so I'm trimming this down to just some of the essential, give you a bit of a feel what our centre is all about, why we're doing research on the human brain, how we're doing it, and what makes us special in New Zealand. And it's because of people like you, believe it or not, and the community and the people of New Zealand who support us that enables us to do what we're doing. So I'm just going to start off first saying a little bit about why the human brain is such an incredible organ. So you see, as it's already been alluded to by Annabelle, I grew up in rural Taranaki. My mum and dad had the general store down there, and we were 5 boys in the family. And looking back, and we've all gone in different directions. One's in international hotels, one's in education, and one's went to the Anglican Church, and one's in healthcare, and I'm in medicine. And you know, the one thing which Mum and Dad gave us, we learned as young kids in the general store, taking the groceries around the community of 100-odd families, and you learnt to work with people. And they taught us, you know, Dad would always say, whatever anyone wants, we will get. We may not have it in the shop today, but we will get it up from Waikato or New Plymouth or whatever. And he said, well, we are on this earth to look after the people. And keep in touch with the people. Never forget where you come from. Don't get too big in the head. Just get on and be the best person whatever you do in the world. And that's fundamental, just good values, good country values. And in a country, you know, in a small country, everyone looks after everyone else. Someone's baling hay. Well, we all used to get around and help bale the hay, and so on. So it's a community thing, and that's the backbone of New Zealand. So all I've done really is take those sort of principles and put them in the brain research. Well, I got interested in how the brain worked, or how the body worked, and you know, I went off to, I didn't know what I was going to do. After first year at Auckland University, I loved maths, but I didn't want to work for anyone else, so very interested in biology and how the brain, how the body worked. I went off to Otago, got into the medical school down there. And as a third year medical student, we saw, you know, you're split up into small groups of 2, and each of you had a human brain to study in third year. Every Saturday morning in those days, from 9 to 12, we would do studies on the human brain. You had a human brain between the 2 of you, carefully dissected, look at it. Well, for me, first looking at the brain on the outside, it is incredible. I should have brought my brain along, and I actually have I have a plastinated brain I use for teaching. I should have brought it along, but not with COVID and a few other upsets with the programs, I didn't have it in my bag. But I've taken it along whenever I do teaching or lectures often. And that's the brain there, which is there. And you know, the pattern of folding is just It's just unique. And everyone in this room, you are who you are because of your human brain. Your human brain is what you are. Your personality, your stamp in life, your memory, your aspirations, everything is there. And when your human brain fails, you fail. And it's the only organ you cannot do without. You can get a new limb, you can get your hip replaced or whatever, but you cannot do without this incredible organ. And what's so special about it? Well, you know, when you compare it with a little rat brain, is this working? There you are, yeah. So this is a little rat brain here, you see? And this is like a baboon brain, really, but monkey brain looks very similar. And that's the human brain. Now, as you go up from the lower animals up to the more complicated, the most complex animal of all, the human, you see what the part of the brain which expands is the front part, what we call the frontal lobe. And the surface of the brain gets bigger and bigger in relation to the rest of the brain. So the only way you can actually accommodate an enlarging outer part of the brain is to fold it. And so if you take a flat sheet, you can fold and get more of it into a small space. So hence, as you go up through the animals, the actual cortex becomes more and more folded. And the human is very folded to fit the maximum amount of brain into that small space, into the space of the skull. And each of those folds are not random folds, they all do different functions. So we're looking at the left side of the brain here. You've got two halves, the right half and the left half. They work together. But like a husband and wife, you know, work together for the common good. And the left side of the brain is very similar to the right side of the brain. It has an area for movement, sensation. And so this movement area on the left side of the brain, this gyrus here, controls all the muscles on the right side of the body. It's the opposite. Why? We don't know. There's no rational reason why that should be. It just is. God knows. That's all. That's all. But we do know how incredibly organised it is. You see, you've got this area down here controls the muscles of the face on the opposite side. Huge area for the lips, the tongue, and so on. And then you've got the fingers, big area for the fingers, because you do all sorts of things with your fingers, your arm. You go up here, then your trunk. You know, your chest and abdomen. You can't do much of that. You don't write with your nipples, or you don't speak through your umbilicus, but those muscles have got a very small area of representation. But then you go to the thigh and the leg, and your foot's over down the middle side. So the representation of your body and the cells of that area is related to the dexterity of control over those areas, you see. And you know, this action, the apposition of the thumb and index finger, humans are the only animals that can do that. And these fine movements of the hand, and they'll be right, all sorts of things. Just think what you do with your hand. And your muscles of your face, you can read a person's emotions by the little changes in those small facial muscles. And so the control over that is huge. And then you just go over that fold, and right at the bottom of the fold, it's like going from the USA into Canada. There is a state line right at the bottom. And when you cross over that, you're in the area of what's called sensation. Now, what happens there? Well, when someone gives you a big fat kiss, you feel it, you sense it here. This is your face area for conscious sensation. That's where you feel it. You may think you feel it on your lips. That's rubbish. You don't. You feel it in your brain. Why do we know that? If this area is affected by a tumour, your lips are numb, you don't feel it. Now you just think, we don't know how it is that the conscious sensation, which is appreciated here, is projected onto your lips. That's an enigma. You learn that, you learn to interpret that, just like if someone drops a big brick on your foot, you feel it up the top here. Right? But it's actually on your foot. So your brain projects this conscious image, but conscious feeling is here. And that is, you know, so if a person has a stroke and affects this area, and this area, you not only can't move your face on the right-hand side, but you also can't feel there. And so you can get little, smaller strokes affecting different parts, see? And the mapping of it here People spend their lives, neuroscientists spend their lives studying the organisation of the cells there. And come behind it, on the left-hand side, the area behind is involved with reading and writing. The left-hand side of the brain, and this parietal area, that's where you learn to, that contains all the computer engrams for you to read, to recognise the spoken word, and also to write. It contains the secret mechanisms that go forward here and stimulate the areas of the brain which control your right hand or left hand, whatever you write with, to write a word. The complexity of learning that. You know how long it takes kids to learn to read and write? Well, this is what they're educating. This is where the cells are multiplying as they're doing that. And speaking, I'm speaking to you now, everyone's got different accents and all the rest of it. That speech is driven by this area here, which you gradually educate, if you like. You educate the billions of neurons in there so that it drives the muscles of your larynx and pharynx and your lungs to talk so you pronounce a word. Now, we can't design. Yeah, we can send men to the moon, we can send rockets up, God knows, to Mars and everything else, but we can't even design anything for that. And this only occurs on the left-hand side. So the left-hand side of the brain is for reading, writing. It's where your verbal language is. Your non-verbal language is in these areas on the opposite side of the brain. Now, what's non-verbal language? Well, I'm looking at you now. Each of you's got a different sort of, you are oozing a different type of emotion. I can read. You know, you each got a different type of where you're excited or whatever. But you can read a person without them saying a word. You can tell by the way a person walks or reacts to you just in their face. You can tell instantaneously whether they love you or whether they hate you or whatever. That's non-verbal language. That's on the other side of the brain. So you see, the only difference between the right and left side of the brain is that verbal language is on this side, the left side, and non-verbal language is on the other side, on the right side. So that if a person has a stroke which affects the left side of the brain, i.e. the right side can be paralysed, they are the people who will have verbal language problems. You won't see a person with verbal language problems, in other words, can't speak, unless it's the right-sided, in other words, a left-sided stroke, right? Follow me? Yeah. But people on the other side, they will have problems with verbal communication. You won't be able to read them. At the front here, you've got memory areas here, you've got the areas for vision. So when you see a picture, half the picture on the right-hand side comes to the left-hand side of the brain, the other half, the left-hand side, goes to the right side of the brain. And they connect up. When you look at the picture, you don't see a line down the middle. The brain pushes them together so you see a continuous 3D picture. And turning pictures that hit your retina into pictures in the brain, because that's where you consciously feel them. That's where you consciously see them. A stroke here, which can happen because of the posterior cerebral artery, you won't see a picture, you won't see the picture, you'll be blind. All comes back there. Memory is here, you know, and there plus other regions too. So your memory of who you are, what you did yesterday, all the way back to the beginning of time, all those memories are stored in this area plus other associated areas. It's complicated. We haven't got a clue how that works. Haven't got a clue. We think we've got an idea, but they're so naive, it's honestly they. And you know, and that associated with this big area, big part of the front of the brain called the, I've just got personality there, but you know, your vision, your dreams for the future, your planning, your executive planning. You know, you get up in the morning, you know what you want to do. And you've got a dream you want to do this, because 10 years time you're going to do this, you know. So all that is here. And you've remembered what you've got planned. You see, so you put all this together, and that's why, you know, rats don't have these areas. Cats don't have them either. They have strong, don't have equivalent areas, because cats, rats and monkeys are doing the same today as what they did 1,000 years ago. They haven't changed. We change continuously, for better or for good. We're always changing. God help us, you know. We're on the move. We're trying to get to, you know, sending bigger satellites up now, bigger telescopes. We want to see to the end of the earth. We want to see where the universe began and all that sort of thing. This is a quest for knowledge. And that comes from this organ. And we take it for granted. I guarantee no one here in the morning, when you were out this morning, no one said, "Thank you, brain. I still know who I am." You know? And yet this is the most important thing in the world. And it's every time I talk about it, I get even more excited. Now, just to give you another little hint, God, I'm going to have to move. We've got the numbers of cells in this brain which we have is 90 billion cells, all right? Look at them from different parts. You've got cells from this area, the visual area, for the motor area, for the memory area. They're all totally different. See, it's one from the motor area, one from the visual area. This turns pictures coming in through the optic nerve into a picture in your mind. And this is memory type cells in the temporal lobe. They're all different. So wherever you go in the brain, the cells are different shapes and sizes, like cars on the road and trucks on the road. They're all different, they do different functions. But they're artistically, they're the most wonderful. I mean, look at them. I just go in ecstasy when you see a cell like that. and each one of those is getting 120,000 inputs. Now, as I said, there's 90 billion cells. We've got about 8 billion people on Earth. If everyone if every brain cell was a person on Earth, that's 10 times the number of people on Earth in your brain. The thing is, they're talking to one another in the most wonderful, integrative way. Each brain cell will get at least 128,000 inputs from other brain cells, and it talks on it. See what I mean? So that's the challenge of brain research, to understand how it works. So no problem, I've got a job for years to come. The challenge, of course, is that we have problems with brain diseases. About 1 in 3 New Zealanders is going to be affected by a brain disease, and these are some of the more common diseases. It's a major problem, especially with the age as you get older. Then the brain does fail, and we need to try and make that and try and stop that. This is Alzheimer's. We've got 70,000 New Zealanders today who are affected with Alzheimer's disease, and it's increasing. The more people go into the older age groups, the more people will be, the greater the numbers are going to be affected. It's going to become a bigger impact. There's no point in living long unless you really know your own mind, unless you can still enjoy the things you love to do. So this is a normal brain down here. It's about 1.5 kilograms. This is one from a person, a 65-year-old person who had Alzheimer's detected clinically for about 5 years, and that person lost 1/3 of their brain cells. That's about 30 billion brain cells. Massive. And you can't detect those changes until they've lost about 1 billion brain cells. So, yeah, there's a lot to do. So, when I started off, I got so interested. I took a year out as a medical student, did a year on brain research. You can only study rat brains. 90% of brain research is 99% of brain research is done on rat brains, because you can't do experiments on the human. And I was just so enamored with the brain. I thought we found a new pathway in the rat brain, published it and talked to a conference, and that's when I got hooked on it. So after I graduated, I went to neurosurgery briefly, and then I realised that even the neurosurgeons didn't know a lot about the brain. They worked on the outside, but couldn't work on the inside. So that's when I started a career in brain research, and went back into the PhD at Auckland. Went over to the States for a few years, 3.5 years, worked at San Francisco, then at NASA base there, then Harvard and MIT, and 3.5 years, came back in 1978 to Auckland Medical School, and started as a young lecturer, senior lecturer there, and I started a little brain project using all the techniques I used overseas, again working on the rat brain, working on the parts of the brain affected Parkinson's and Huntington's. And one day a family came along to me, actually through the professor of genetics, Arthur Faull, and about 3 years after I got back in 1980 it was, and said, "Listen, Richard, you're working on this part of the brain affected in Huntington's and Parkinson's, and I look after all these families out there." Professor Faull said, "Who've got Huntington's disease. It's a genetic disease. It's caused by a gene. And if they got the gene in the family, it's a dominant gene. So if the mum or dad have the gene, they will get the disease, and 50% of the kids will get it too later in life." and about the age of 45 or 50 they'll see the first symptoms and they'll be dead in 15 years. He said, we can't test for the gene, we can pretty well see whether or not clinically they have the disease, but we can't be certain. Because they'd love you to look at the brain of their mum or dad after they die, just to make sure it is really Huntington's disease. So they said, would you look at them? I said, yeah, it'd be great. I'd be very pleased to do that for them. And then and so in most cases we said, yeah, they actually did have it. The pathology was clear, they certainly did have it, and they obviously had the gene in the family. Others, a few of them didn't, which was wonderful news for them. But what those families did was said, well, keep the brain and do research on it. And that, I didn't realise that was going to change my life forever. Because I shifted from the rat brain over a period of 10 years to the human brain, studying not a model, but the ultimate model. And so we began looking at the human brain and found some wonderful things, which I'll tell you, just a few of the interesting findings I'll tell you about in a moment. But not only did we do it in Huntington's disease, we learned so much that the books were wrong. They said Huntington's was a single gene disease, every brain looked the same. We found no, they didn't look the same, they were different. We then expanded into Parkinson's, Alzheimer's, and linked up with the families of New Zealand, you see. And ultimately in 1990 we were getting a collection of brain tissue from families with different types of brain diseases which the person had died of. And I thought, it occurred to me, I thought, we're getting a bit of a bank of tissue, we should call it the human brain bank. Now, we didn't have any money for it, so we went to Neurological Faull and I said, listen, we've got a human brain bank, would you give us some more money to staff it, and we'll give you the name. So there we are. So now we are, 30 years later, there are over 1,000 tissue from over 1,000 brains, work closely with the associations and also very closely with the families. And we receive requests from all over New Zealand. And we've depending on the circumstance of the death and the time of the week and the weekend and all the rest of us, whether we can receive it, we have to be very selective. But because families in New Zealand, this gets back to when I was a kid in Taranaki, I said, Mum and Dad said, look after the people. We found that the people were looking after us actually and providing us with the most unique research source to do things which no one else in the world could do. Because we kept in contact with the families and we realised soon through Lynette Tibbett and others that looking at the brain and seeing how the brain cells were dying was one thing, but we needed to know the track record of what that person's journey in that disease in life was. In other words, what were the symptoms? And then we could understand their pathology. So knowing the person's symptoms, whether it be Huntington's, Parkinson's, epilepsy or whatever, we could then understand, and you had to know them precisely. So we had to go back to the families, get that, and the families loved giving us all this information. You had to go back to the doctors, bring your doctors in to help us, clinicians and neurologists and neurosurgeons, and put all that together. And you can only do this in a small country, you see. So we had a human brain bank, which is quite unique. The families are so committed, we got this tissue that they were registered with us. The person with the disease often registered way before they died, and they knew, we told them it was critical we get the brain as soon as we could, and they would link up with the rest home or whatever to make sure that we would call very quickly, so we got the tissue within 2.5, 3, up to 12 hours after death, and that is incredible. No other brain bank in the world has that. So the tissue is high quality, but it's a partnership between families, doctors, clinicians and researchers, and so it's given us a resource which has made us world class. That's the actual room where we dissect the brain up, and I haven't got the slides, but we worked out a unique technique of preserving and cutting the brain into small blocks like a Lego, 60 blocks of each side of the brain and so on, and each is stored in a way that can be preserved in -80 freezers. We've got over 40,000 blocks now, from over 1,000 different brains. So this has led us, because we've had this wonderful human tissue, in an unconscious way, we had our colleagues overseas that hear us talk at conferences, and they come and say, oh listen, can we have a little bit of tissue to do this technique, or look at these genes, or do something else, which we can't do in New Zealand. Went back to the family and said, do you mind if we send a bit of tissue overseas? to the group in Oxford, Cambridge or New York or London or wherever, Boston, to do studies, and they'll be collaborating with us, so that they can look and see from their research expertise, find out more about the brain that we can't find in New Zealand. Every family has been absolutely enthusiastic. They said, you know, it's like mum's getting the travelling best she never had in life. Or, you know, it's just saying, you know, dad's living forever, you know. There's research is going on using his brain tissue to help our kids. And so these are just a few of our groups. I won't go through them in detail, but there's some groups in the UK. These are groups in Sweden and Switzerland there, and United States and Canada. And that's just and these are, I just been to a conference 2 weeks ago, met most of these people actually, and who we're working with and we continue to publish papers with. So you see, through that, unconsciously we have established a sort of a, if someone said when I, they say, what are you going to do when you grow up? Oh, I'm going to be a human brain scientist. I'm going to head up the Centre for Brain Research. What a load of rubbish. Well, just following your nose is what we did. And so we got, when we first formed the centre, we formed the centre because we realised that we were collaborating with different groups in the university, all doing brain research. I said, well, we should form ourselves into a unique club across the university called ourselves the Centre for Brain Research. So in 2009 we launched this because we were working collaboratively together. You've got to have a, I didn't realise it, but marketing is, you've got to work under a single name and sell yourself. Not sell yourself because you think you're good, but sell yourself so that they can help you. And so in 2009 we started with 25 research groups. Today we have 84 research groups. We have over 450 people, all in the Centre for Brain Research at the University of Auckland, and they are the senior researchers, the PhD students, the postdocs and all the rest of it, but they work together. We've redesigned labs so that people actually work as teams, because just like the All Blacks, when they win fantastically, and we want to win all the time, of course, and so I always call us, well, we're a bit like the All Blacks of brain research, and everyone's got their different jobs to do, put it all together. Maybe one person will score a try this week, maybe another one next week or whatever, they can't do it without everyone else, you see. And so you've got the geneticists, you've got the chemists, you've got the pathologists, you've got all of us all working together across the university. And then of course, that's the main pillar, but we have all the doctors, the neurologists and neurosurgeons in the hospital. That's our clinical pillar, way part of us. And all the families in the community who have suffered from brain disease, who help us enormously by giving us this brain tissue, they are the art. And so those three pillars are what we are, and that's quite unique. There's no other centre in the world that's like us. And we have great overseas collaborations. I've just got a few slides to go.
Just relax, Richard. Plenty of time.
Is that right?
Yeah, we'll go.
So, just a quick sip. So let me tell you a couple of things. I'm sure every one of you in this room, in your careers, you've ended up doing things and going in directions that you didn't ever expect, right? And when you think back what you were doing, when you were in your late 30s, and what you thought you were going to be doing 10 years later, probably quite different. Same with our brain research. So this is a brain from a person who died of Huntington's disease. And this is a normal brain from a person who died with no neurological disease. It's just as important to get normal brains as it is to get Huntington's or disease brain, you see. So we started off looking at these brains, and we found absolutely fascinating things. We found, for instance, that the pattern of cell death early on in the Huntington's brains was not consistent from one case to the other. There was huge variations in the actual pattern of cell death in this area called the basal ganglia. None of the textbooks said anything about that. And that's where I had to talk to Lynette Tibbett, and I said, listen, Lynette, we're finding from these cases that there's a lot of variation. And that's when she suggested, well, go out and talk to the families. And so she took her team out, and they collected the history of every single Huntington's brain we'd collected over the years, and got the background history. you know, how much mood these patients had, how much movement problem they have, and all the rest were catalyzers there. And when we got that together, we found that the variation in the pathology there reflected the variation in symptoms. Now, you might say, well, that's pretty obvious. Yeah, it was. It is pretty obvious. But that meant we can extrapolate back and say which particular cell groups were involved mainly with particular types of movement, aspects that these patients can get, or particular types of mood they can get, because they all vary, you see. And so we were using the human brain in a reverse way to how we did experiments on rats. And rats, you go and knock out a small bit of the brain, see how that changed the animal's behaviour, then cut it up and look at it and see exactly what you knocked out. Here, we were getting the brain at the end of a person's life. They'd gone through a disease process. We were looking at it, and we could use their symptom profile, their development of their abnormal symptoms, and relate it to exactly what parts of the brain. Therefore, we could conclude what parts of the brain do what with the movement or mood. See what I mean? And so, and we didn't realise. It took me a while to realise that. And so that was one huge area of activity. But something else happened when we began to look at just this area of the basal ganglia right next door to the ventricle. You see how this gets shrunk down? Normal size, it's nice and big. I hope mine's just like that. When we looked just at the edge here, we found things which are puzzling. We found that there were new brain cells being made. And kind of a 5-year huge program down, we found that in the Huntington's brains, the cell death in the basal ganglia underneath here was stimulating new brain cells being made. And we knew in the rat brain that, and this is the normal brain of a human, there's a few cells there. We discovered they actually are stem cells left over from when we were all fetuses. We all have these adult stem cells lying here, just in. See, they lie just there. We discovered that we have stem cells lying here, left over from when we were a fetus, and those stem cells can make new brain cells. Now this was controversial. People didn't believe that. But we found that in the Huntington's brain, because cells were dying here, those stem cells were kicked into action, and although they weren't making enough new brain cells, they were making new brain cells. Now this was revolutionary. And it was incredible. And we knew this happened in the rat brain, and we knew in the rat brain there was a motorway going down through the middle of the rat brain where these new brain cells would go. It was a pathway going down to the middle of the rat brain. So we thought, well, if this is happening in the human like it is in the rat, it must be a motorway. So we searched. It took us 5 years to find this motorway. And it's distorted, it goes around, bends back on itself because the human brain has developed and got so big in the front here, it's distorted the motorway. So a bit like I always describe the motorway as going from Auckland to Wellington, you know, and the rat in the course of the human brain because this huge development of the cerebral cortex that goes down around Mount Taranaki, you see, sort of sideways. And so we discovered this and we thought, wow, we've got to publish this now. Tried Nature, and of course this was, everyone was told, and you people may well remember that, you know, you're all told the human brain can't make, once you get to maturity, you've got the brain cells for life, use them or lose them. You know, if you don't, you're going to get dumber and dumber as years go by, all right? And we were basically attacking that whole dogma. So we sent it to Nature, the top journal, two top journals in the world, Nature and Science. Nature's in the UK, Science in the United States. Sent it to Nature. They sent it out to the top leaders in the field, and of course, the top leaders in the field, first they thought, who the hell are these young Kiwis thinking who the hell they are, you know? You know, we've been studying this forever, and we've never ever seen anything like this, and they didn't believe it. They said, well, you know, I only believe it if you can actually grow these big slices in the lab, in the human brain, and show these cells making new brain cells and migrating down this pathway. Well, you know, we've only got one life, so we did more studies, and then we packaged it again differently and sent it to the other journal, Science. So long story short, we got it in. Yeah, and on the front cover, this is 2007, and this created all hell but loose too, because this was changing and saying that the human brain, just like all the animal brains, we have the facility to make new brain cells forever. You may make less of them as you get older, but those stem cells left over, those adult stem cells left over from when you were a fetus in your mum's womb, are still there, and they have the capacity to actually make new brain cells. This was revolutionary and controversial. We got attacked at conferences, and until other groups in the world actually repeated it, and then it's now accepted. So your brain is plastic, you see, it's continuously changing. And that has huge implications. When you think of it, it's such an obvious thing. As you accumulate more knowledge, your brain must change. And therefore, we don't quite know how changes in brain cells and numbers of brain cells, we don't know how that occurs because you can't do these detailed studies on the human brain. But on animal studies, we've known for years that the more you exercise and stimulate the brain, animals, put animals into a cage and let them just run around, or put them into a cage where they've got lots of things to do, playing the running wheel and all the rest of it with rats, they will make new brain cells, or exercise makes new brain cells. And they will make up to 40% new brain cells. If you do too much exercise, if you stress it in the exercise, we found the rats make less brain cells. So it's all to do with proportions. But the concept that because it happens in rats, and because we have found we've got the same facility in humans, then we believe that we can make new brain cells forever. Keep your brain stimulated, creative thinking, and I like to believe creative thinking makes new brain cells. We're probably waiting for you this morning. So use it or lose it. And so that's changed the dogma completely. Great to hear in our mature years of our life. So we're looking to see if they're coming off this motorway, we're looking for other off-ramps which may be able to activate Parkinson's and Huntington's disease and so on. The second major technique which actually influenced our research in the Centre for Brain Research is that we over the last 15 years, we have found that we can take human brain tissue, as long as we receive it soon after death, or if we get it straight off the operating table from the neurosurgeons, we can take it into the lab, cut it up into very small pieces, and what we call dice it up, and then digest it with enzymes, so you separate the brain cells and make it sort of a suspension of brain cells, and build them into a culture, put them in the oven and keep them at 37 degrees and so on in a specialised medium, and we can keep brain cells alive. Really? Yeah, and now it's taken 10 years, and it's not just one type of brain cell, but all the different glial cells, all the different neurons, but they're very hard, but we can do it. And then once you do that, you see, we can't build brains because these cells are isolated and separated, but we can take cells from a person with these. This is what healthy brain cells look like, just kept alive in the lab, all disconnected. From a person with Alzheimer's disease, they're very different. So we can take those, you see, and we can trial new drugs in the lab. It's not against rat brain cells. Pretty well every drug that's been developed in the rat for Alzheimer's disease has failed in the human. And you just have to look at the difference between a rat and the human to understand why. So if we don't study the human is going to be, that's who we want the drugs and treatments for. You've just got to work on the human as much as you can. And so you see, we can use these to develop new treatments, trial new drugs, which we're doing right as I'm standing here now. So, the two major areas where we've made huge impact is showing that the human brain can make new brain cells, and we can culture the brain cells from all the different types of tissue we get now, and we can trial new treatments and get new drugs. And that's opening up a huge, and also what we're doing now, we're developing clinics, research clinics with the different diseases, so that we're studying people in the very early stages of Alzheimer's, for instance. We've got what's called the Dementia Prevention Research Clinics. We've got a clinic in Auckland, there's a clinic in Christchurch, a clinic in Dunedin. and we're want to enroll about 400 people. We've got over 200 people so far in the very earliest stage of the disease, and we sort of put them through the ringer, and so to speak. We do MRIs, we do blood tests, we do imaging studies, we test and see what their symptoms are, talk to psychologists, talk to neurologists, and we get a profile of what their disease is right now, and then we monitor them, and then we can use them, because once we know what the progress they're making in the early stages of the disease, and we use blood samples to see if there's any markers which will say what sort of stage of the disease they're at, and then we trial them in a treatment trial and see if we can slow down the appearance of those markers. If you can slow down Alzheimer's by 5 years, we would drop the prevalence of that disease by 50%, because people would live longer, more switched on, and die of something else. So push a disease out past their normal death. I mean, if you can't cure it, I mean, it's such a complicated disease, we won't be able to cure it for years, if ever. But push it out, so they die of something else but still know who they are. Then that's as good as a cure. And I never realised, I didn't realise about 10 years ago that this is, people would say, oh, you've got a cure yet. Well, no, but if we can delay it, if we can use gene therapy, we just appointed a new professor, I don't know whether you saw Monday morning's Herald, but we've just appointed the world leading gene therapy scientist from London. He's actually New Zealander, went into neurology here, then went overseas, and over the last 25 years he's world leading in gene therapy for motor neurone disease and other types of neurodegenerative disease. He's got a big company over there, and they're trying their very first gene therapy where they're injecting new genes into the brain. And so this is where we're at now, and it's wonderful because we can do this in New Zealand better than anyone else in the world. He's got to retain all his links in the UK, so we won't lose any of his great studies he's doing over there. The last slide, here we are. So these are the risk factors for Alzheimer's and brain disease. These are the protective things. So stop smoking. High blood pressure, get it treated. If you've got diabetes, get it treated, because those things will clog up your arteries and cause problems there, which is not only to your heart but to your brain. Keep mentally and cognitively alert. Keep thinking, keep using your brain. Physical activity, you don't have to run a marathon every day, but do a bit of walking, 40 minutes a day. And just enjoy life, but do what you like. You don't have to run yourself into the ground, but just turn it in and just do a bit more physical exercise than what you do. What you're doing here, social interactions is the most powerful thing ever. Get together, talk about people. Don't go into your own mind, go into other people's minds. See how you can help people. That type of interaction is critical. Reduce depression and stress. Correct your hearing. We know that if you have a hearing problem, that increases your risk of dementia, but if you get it corrected, that will stop that. Diet, Mediterranean diet, you've heard all this before, and no moderate. You don't have to cut out alcohol, but you don't have to drink a whole bottle a night, Just do things in moderation and enjoy. But as I always say, you've got to just enjoy life. And also, I mean, it's crazy in the world, like we've got so much to live for, and we've got maniacs like Putin trying to shoot someone. What a crazy outfit it is. So we're lucky to be in this part of the world. So you see, we are the Centre for Brain Research in New Zealand here, because of the way we work with the community and with the people, and get huge support from philanthropists. We get about $5 million a year from all the different groups around who support us in all different ways, the Freemasons, the Douglas Trust, Douglas Pharmaceuticals, and the Hugh Green Foundation, and many others. And people just give us money just because they believe in us, and we are, as I say, it's a partnership, and we bring them in every year and show them what we're doing and what we can do with their funds, and we love it. So sorry I've gone over time, but thank you for the pleasure to come and talk to you.
Yeah. Richard, would you like to take some questions?
Yep, absolutely.
I once thought that I was told that there's 40% of the brain that we don't even know what it does. Is that still
rubbish? Yeah.
Is that rubbish?
Yeah. So, you can take an MRI of the brain and see which parts of the brain are active. when you're doing particular activities. And sure, they are very busy. But it doesn't mean to say the others are, it's the background activity, and it's big, like a big city here. I mean, when there's a big thing going on at Eden Park, you say, oh, everyone's at Eden Park. Well, actually they're not, you know. The city is still going. So the brain is still working, you can't, and so yeah, you use every single part of your brain. Different parts are more critical for particular function than others. But you can't, it's a bit like, you know, sawing off the suburbs walk and saying, well, this suburb's not doing a hell of a lot, we'll just get rid of it, you know. Well, everyone is contributing in a team-like way to keeping the brain going, and you need different parts of it. When you go to sleep at night, it's damping down so you can rest and so it can recover. But it's not saying it's not useful. So it's an ignorant comment, actually.
Richard, I've got a question.
Yep.
You spoke about moving from the rat to the human brain in your research here. So were New Zealanders the first to do that?
Now, other overseas have done it in different ways. Not in as organised a way as we have. I mean, we still work on the rat. It's really important for things you cannot do on the human brain. So put the two together is really important. It's just that we end up, because we developed a close association with family that had their sport, we've ended up with a human brain bank, which the tissue is so incredibly useful for research because we get it very soon after death. We get it with all the added information from the family, so we've got a huge amount of information. There are brain banks in New York and Boston and Zurich, and they are just banks of tissue of a person with Parkinson's, painters, or whatever. But they don't have this added value of information, you see. And we can actually pick up the phone and talk to any family up and down New Zealand and get more information if we need it. So, being in a small country, sometimes, you know, small countries can do better things sometimes, better and faster than other countries. And this is where you turn your so-called perceived disadvantage into an advantage. And so it wasn't planned, it just happened, you know. That's why I say never plan your life, just get on and take every opportunity that comes along to you.
Richard, people, if there's anyone who wants to be involved in the study where you're looking at the front end of early symptoms, how do they connect with that?
Well, so we've got a special, you just Google the Dementia Prevention, DPRC Clinic, Auckland University, and we've got a special person there who will make contact and just go through and talk to the family and see whether or not their mum or dad, whoever it is at the stage where they are in the early stage. Because sometimes we get people referred to us, and when we do when we get the history and all the rest of it, we find they're actually more advanced, unfortunately. And that can be it can be not good for the people too. It's very hard, so we've got to manage this. So we have to be very selective because it costs there's enormous resources required to follow these people through on an annual basis. You just Google to find it.
Thank you, Richard. Thanks this morning in the hands of Gabby.
So Richard, first of all, we wanted to thank you for coming out this morning and getting up early and being here with us, and sharing your incredible enthusiasm for your research. And it's everybody here today, their brains are working overtime. And you'll put us in overdraft for the rest of the day.
Well, it's probably all my new brain cells.
Yeah, that's right. But thank you so much for being here and sharing your knowledge. And Rotary just appreciates you being here just with a small gift of a pen.
Thank you
very much. To use.
Thank you.
And good luck in your future things.
Lovely. Wonderful.